Then let's resume our lecture on computer science of continuous data, algorithmic foundations of numerics. And we're now entering section 2 about real computability. So qualitative theory of computing with real quantities. Real quantities include real numbers, real sequences, real functions, real operators, and real, that is Euclidean subsets. And today we will introduce and compare several natural notions of computability for real numbers. And that's important because having the right notions is crucial. So let me show you the slides. So chapter 2, computability over the reals. And that includes, starts with talking about what it means to compute single real numbers. We will consider three notions that are all natural, and fortunately all three of them turn out to be equivalent, which is good news because it means we don't have to decide or to choose between three different but reasonable notions. And this is also strong evidence that all these three notions are reasonable notions, because when three entirely different approaches turn out to be equivalent, then it's a threefold evidence of being reasonable, of being the right notions. And that's crucial in mathematics because there are many examples where people have initially considered unsuitable notions and later had to adjust them. Okay, and then we're going to talk about examples of computable real numbers and counterexamples, real numbers that are not computable provably. And this is really far beyond classical numerics, which is somehow focused only on positive results, namely on computing things, right? But being able to prove that something is fundamentally impossible to compute, that is only possible in science, not in engineering. Then we're going to consider Oracle computable reals, that is real numbers that are computable when we're given Oracle access, when we have while programs that can Oracle access to the halting problem, for example, or higher undecidable problems like the halting problem prime, as you recall from the previous chapter, or the totality problem, or so on. And then we're going to proceed to the next data type that you're familiar with from calculus, namely real sequences. We talk about what it means to compute a real sequence, and then we discuss what it means to decide equality of real numbers. As you recall, this is a common folklore in numerics. Don't test for equality. There, the justification is because of the rounding errors of floating point numbers, but here we will be able to prove rigorously that it has nothing to do with floating point numbers. It's really fundamental. It's actually equivalent to the halting problem, to be precise, to the complement of the halting problem. Classically, we know that there are only countably many algorithms, there are only countably many decidable subsets of natural numbers, there are only countably many computable real numbers. So the common question is, natural question is, can we put them all into a sequence? Well, that's of course true, but can we put them into a computable sequence? And that, interestingly, turns out to be fundamentally impossible again. There's no computable sequence that contains all reals. And we proceed even further up in the type hierarchy: real numbers, real sequences, real functions. We define what it means to compute a real function, and then we investigate closure properties as evidence again for this definition to be reasonable. What we want is that the composition of computable real functions to be again computable, the restriction of a computable real function to be again computable, and we investigate what happens if we plug into a computable function a computable real sequence as defined previously. And then we discuss some uncomputable operations, maybe like the operation of root finding turns out to be in general uncomputable in a very strong sense. And there will be more uncomputability results, such as, for instance, a solution to the wave equation or calculating derivatives of continuously differentiable functions, and more rigorous uncomputability results revolving around functions. Then we're going to talk about multifunctions. Right. Functions first. It turns out that every computable function is necessarily continuous. And for continuous functions, we have the Weierstrass theorem. And there's a computable counterpart to the Weierstrass theorem, which we will learn about and prove. And that proof involves the important observation about compactness in a real computation. That's a new aspect that is not present in the discrete realm. Discrete subsets are finite subsets and therefore in a sense trivial, but in the real case, compactness is a real non-trivial property, and we're going to investigate how that enters in real computation. And then we get to the multifunctions, which is a kind of oxymoron, namely a multifunction is a function which violates a functionality which violates the extensionality property. And we will discuss some notions, extend some notions from functions to multifunction, specifically the notion of what it means to be a restriction will be and have to be generalized. And as example multifunction, we'll consider the fuzzy sine function and a multivalued counterpart to the Archimedean property. And we will see that in this way, proceeding from function to multifunction really makes a difference between uncomputability and computability. And then we'll discuss what it means to compute real operators as the next step up in the type hierarchy. Real numbers, real sequences, real functions, real multifunctions, real operators. And this requires that we agree on how to encode functions as arguments. How can we input a function into a while program, a real function? And how can we input a compact subset into a while program? And this will be the last part of this chapter 2 on computability theory over the reals. And to be warned, this is going to be a long chapter. This is our carefully chosen excerpts from the textbook of computable analysis by Klaus Weyrauch, adjusted and adapted for the pedagogical convey in a lecture like this. Okay, let's get started. What should it mean for a real number to be computable? We know what it means for a subset of natural numbers to be decidable, or what it means for a function or natural numbers to be computable. But now we need a new notion actually, and there are three natural notions actually that come to mind. The first notion dates back to Alan Turing. Maybe we look at the binary expansion of that real number. Binary expansion, we say that the real number is computable if it has a decidable binary expansion. And right, what does it mean to have a decidable binary expansion? It means let's write down the real number with its binary coefficients and then ask, given a certain index to this binary expansion, is the corresponding coefficient 0 or 1? And that's a decision problem, right? So this is a decision problem. Here we consider the binary expansion of that real number, right? Let's say it's a real number between 0 and 1. This is its binary expansion. and Bn are the binary coefficients, which can be 0 or 1. And the decision problem, a subset of natural numbers, asks, given an index, is the corresponding coefficient in the binary expansion 0 or 1? If it is 1, then answer yes. If it's 0, answer no. That's a decision problem, and the set of those indices where the answer is yes, that's a subset of natural numbers, that's a decision problem. So in this definition reduces kind of the notion of real computing to a discrete notion of deciding something. This is the notion introduced by Alan Turing. But there are other reasonable notions that have been maybe formalized approaches from numerics, such as requiring or asking for a real, given a real number, whether it is possible to approximate that real number. Approximate it, let's say, for instance, using dyadic ratios, that is, fractions of integers where the denominator is an integer power of 2. Such approximations are the ones that are used, for instance, in floating point computation, where n is the length of the mantissa. So this is not your ordinary floating point computation, but actually computing a sequence of floating point numbers of increasing mantissa length n. So n tends to infinity, such that this floating point number approximates the real number up to decreasing error 2 to the minus n. That's the second notion. And the third notion was introduced here by Andrei Gregorczyk, namely approximating again the real number with the error bound, but now the error bound can be arbitrary, not just 2 to the n. This is kind of like fast convergent approximation. And this is arbitrary approximation, but computable, namely the sequence of error bounds Cn must be a computable sequence. And also here, Gregorczyk relaxes that now both numerator and denominator can be arbitrary integers, provided that the sequence of numerators and denominators is computable. And here computable, of course, here in item B and C, computable means in the classical sense as discrete objects, computable by while programs. And so these are reasonable notions, these are natural notions, and the question is which one should we use? There's also a fourth notion that often occurs in numerics, namely computing a sequence of rational approximations, just like in the sense of Gregorczyk, but without error bounds on the quality of approximation, sequence of rational approximations that just converge, eventually converge. And this turns out to be, well, at least a much weaker notion. I'm not going to say it's unreasonable, but it is going to turn out to be much weaker than the other three notions. The other three notions turn out to be equivalent, but the fourth notion, if you recall, this is basically the same as Schoenfield's limit lemma, right? So this is just a limit eventual convergence, and from Schoenfield we know that this is this is so weak that it corresponds to being given oracle access to the halting problem. So this is a very weak and impractical notion in many sense. And this has been proven by Ernst Becker. Here you see a picture of Ernst Becker, Swiss logician. So here you see three famous logicians that have made significant contributions to real computability theory. And I'm going to prove this theorem and going to prove the equivalence of these three notions in a few minutes. Well, no, it turns out we're running out of time. So let me wrap things up. So we have these three notions of computability for real numbers, and in the next session, we're going to prove that the first three are actually equivalent, and we're going to prove Specker's result that the last notion is equivalent to compute to any of the first three, but with oracle access to the halting problem. And then we proceed from there to see examples and counterexamples of computable and uncomputable real numbers.